This week in Environmental Science, we'll be taking a look at Chapter 10, which is on environmental health and toxicology. Our objectives for the chapter are to understand environmental health and environmental hazards, to understand toxic substances in the environment, the movement of toxic substances and their effects, to understand chemical hazards, risk assessment and risk management, and the philosophical approaches to risk. Our central case study for the chapter is on bisphenol A, also known as BPA. It's everywhere, but is it safe? How is it that a chemical found to alter reproductive development in animals gets used in things like baby bottles? How can it be that a substance linked to breast cancer, prostate cancer, and heart disease is routinely used in food and drink containers? The chemical bisphenol A, or BPA for short, has been associated with everything from neurological effects to miscarriage. Yet there's better than a 9 in 10 chance that it's coursing through your body right now. Bisphenol A is an organic compound. Its chemical formula is C15H16O2 and was synthesized in 1891. As they began producing plastics in the 1950s, chemists found BPA to be useful in creating epoxy resins used in lacquers and coatings. Epoxy resins containing BPA were soon being used then to line the insides of metal food and drink cans and the insides of pipes for our water supply, as well as in enamels, varnishes, adhesives, and even in dental sealants for our teeth. Chemists also found that linking BPA molecules into polymers helped create polycarbonate plastic, a hard, clear type of plastic that soon found use in water bottles, food containers, eyeglass lenses, CDs, DVDs, laptops, and other electronics, auto parts, and sports equipment, including baby bottles and children's toys. With so many uses, BPA has become one of the world's most produced chemicals. Each year we make about a half a kilogram of BPA per person on the planet. Unfortunately, BPA leaches out of its many products and into our food and water and our air and our bodies. So we could fully say that 93% of Americans carry detectable concentrations of BPA in their urine, according to the CDC, or the Centers for Disease Control. How does it work? Well, there's been a lot of studies with laboratory animals, and the health impacts from BPA include a wide range of reproductive abnormalities. This is because BPA mimics estrogen, which is a female hormone primarily, and the body reacts to it as it would estrogen. Researchers and doctors and consumer advocates want governmental regulation, but still the chemical industry insists that it's tested it itself and that it is safe. Some countries have actually banned it, including Canada, where it's banned altogether, and Japan has banned it altogether. In some nations like the US, we restrict its use with babies and small children only. So for the rest of us adults, we are in contact with BPA probably on a daily basis. Because of the mounting safety concerns, there is some speck of good news, such as Campbell's company has announced that it's transitioning away from using BPA in their soup can liners. And food giants Conagra and Nestle and Heinz have pledged to remove BPA from their food packaging. Bisphenol A is by no means one of the greatest environmental health threats out there, but it does give us an example of how we as a society assess health risks and decide how to manage them. As scientists and government regulators assess BPA's potential risks, their efforts give us a window on how hormone disrupting chemicals are challenging the way we appraise and control the environmental health risks that we face daily. The broad field of environmental health is one that assesses the environmental factors that influence our health and the quality of life. These factors include both natural and anthropogenic or human-caused factors. Practitioners in environmental health try to prevent adverse effects on human health and ecological systems. We face four main types of environmental hazards. The first one is physical hazards. These occur naturally in our environment and can include things like UV radiation, earthquakes, volcanoes, fires, floods, landslides, hurricanes, and droughts. We can't prevent them, but we can prepare for them with proper planning and in some case avoid causing them. We increase our vulnerability by deforesting slopes, which then would increase the chances of landslides. And when we channelize rivers, this increases flooding. In the picture, we can see one example of a physical hazard due to the exposure from UV radiation, which would then cause a sunburn. The next type of hazard we face is chemical hazards. Synthetic chemicals like pharmaceuticals, disinfectants, and pesticides, and even some natural chemicals like lead can be harmful to us. There's also number 3, biological hazards. These result from ecological interactions, such as infectious disease from pathogens like viruses and bacteria, or from parasites that parasitize humans like malaria and cholera. We can't avoid risk, but we can reduce infection through monitoring, sanitation, and treatment, and educating others. The fourth type of environmental hazard we face is cultural hazards. These result from where we live, from our socioeconomic status, from our occupation, or from behavioral choices. We can minimize or prevent some of these hazards, whereas others might be beyond our control. For instance, secondhand cigarette smoke might be something that's hard to avoid for some people. Much of the same might be said for other cultural hazards like diet, nutrition, criminal behavior, and workplace hazards. Environmental justice advocates argue that forced risks from cultural hazards, like living near a hazardous waste site, are often higher for people with fewer economic resources or less political clout. Despite all of our technological advances, disease causes the vast majority of human deaths worldwide. Over half of the world's deaths result from non-infectious diseases. Those are ones that are not spread from person to person and include things like cancer and heart disease. These diseases are influenced by genetics, environmental factors, and lifestyle choices. Of course, poverty and poor hygiene help to foster these illnesses. Although infectious disease accounts for fewer deaths than non-infectious disease, infectious disease robs society of more years of human life because it strikes people at all ages, including the very young. Infectious diseases are ones that can be spread from one individual to the next. They account for almost 1 out of every 4 deaths that occur each year. Infectious diseases are a greater problem in the developing countries, where it accounts for close to half of all the deaths. Infectious diseases cause many fewer deaths in developed nations because they have better wealth, which allows for better sanitation, better hygiene, and better medical care. The leading cause of death by infectious disease is respiratory infections, as we can see from the chart in the corner of the slide. Many infectious diseases are spread by what's called a vector. This is an organism that transfers a disease to a host. AIDS is a well-known infectious disease, but respiratory and diarrheal diseases claim far more lives every year than AIDS. According to the figure, how many times more lives were lost to respiratory infections and diarrheal diseases than to AIDS? See if you can use the graph in the corner of the slide to find the answer. Decades of public health efforts have lessened the impacts of infectious diseases and have even eradicated some. But some diseases like AIDS or acquired immunodeficiency syndrome continue to spread globally despite our efforts to stop them. Others, like tuberculosis and strains of malaria, are evolving resistance to our antibiotics. Additionally, human-induced global warming is enabling tropical diseases like malaria, dengue, and cholera to gain footholds in our temperate regions. In our world of global mobility and dense human populations, novel infectious diseases, or new strains of old diseases, that emerge in one location are more likely to spread quickly to other locations. Some examples include the H5N1 avian flu that emerged in 2004 and the H1N1 swine flu that spread across the globe in 2009 and 2010. Diseases like influenza, whose pathogens evolve rapidly, give rise to a variety of strains, making it more likely that one may turn exceedingly dangerous and cause a global pandemic, which is a widespread outbreak of the disease. There's many ways to fight infectious diseases, and we can reduce the chance of infection through immunization, sanitation, access to clean food and water, security, and by education. Toxicology is the study of chemical hazards. Our modern society is exposing us to more and more synthetic chemicals as we begin to make more and more of these in industrialized nations. Some of these can pose threats to human health, but figuring out which ones do, which ones don't, and how and to what degree is pretty complicated. Toxicology is the science that examines how poisonous chemicals affect the health of humans and other organisms. Toxicologists assess and compare substances to determine their toxicity, or the degree of harm a chemical substance can inflict. A toxic substance or a poison is called a toxicant, but any chemical substance may exert negative effects if we expose ourselves to enough of it. So quantity always plays a role. As more and more people are concerned with exposing ourselves and the environment to toxicants, the field of environmental toxicology has grown. It deals specifically with toxic substances that come from or are discharged into the environment. Toxicologists generally focus on human health and use other organisms as models and test subjects, such as mice and plants. Most environmental health hazards actually exist indoors. Most Americans spend 90% of their time indoors. Cigarette smoke and radon which can occur indoors, causes lung cancer. Mold can occur indoors, in homes and in offices, and produces toxic compounds that can have negative effects on human health. Asbestos, which is used for insulation, can cause problems if inhaled. Lead pipes and gasoline damages organs and causes learning problems, hearing loss, and death. Education and phase out has decreased lead poisoning. One recently recognized indoor hazard is polybrominated diphenyl ethers, or PBDEs for short. These compounds are used as fire retardants in electronics like computers and televisions, in plastics and furniture, and they evaporate very slowly over the lifetime of the product. Like bisphenol A, they act as hormone disruptors. And animal testing suggests that they can also cause cancer and affect thyroid hormones and have a negative effect on brain and nervous system development. Concern about them rose in the 1970s to 1997 when they found that concentrations of these compounds in the breast milk of Swedish mothers rose exponentially. So the European Union banned them in 2003, and concentrations in breast milk has declined since. But yet the United States has yet to make any decisions on banning this chemical. Risks must be balanced against rewards. We have to remember that in our industrialized country, chemicals have given us our high standard of living. Industrial agriculture's production of food, medical advances that protect our health, prolong our lives, and in modern materials and conveniences that we've known to grow and love as humans. So we need to remember the benefits and then weigh the negative side effects and search for better alternatives. Our environment contains countless natural substances that can pose health risks, including things like oil oozing naturally from the ground and radon gas seeping up from bedrock into our homes. Toxins are toxic chemicals manufactured in the tissues of living organisms. For example, chemicals that plants use to ward off herbivores, or insects that use toxins to defend themselves from predators. In addition, though, we're exposed to many synthetic or human-made chemicals. Synthetic chemicals surround us in our daily lives. The United States manufactures or imports around 113 kilograms or 250 pounds of chemical substances for every man, woman, and child. Many of these are particularly pesticides and insecticides. These find our way into our soil, air, and water, and into humans and other organisms. In fact, the U.S. government's latest National Health and Nutrition Examination Survey gathered data on 148 foreign compounds in Americans' bodies. Among those were several toxic, persistent organic pollutants restricted by the international treaty. Depending on the pollutant, these were detected in 41 to 100% of the people tested. Our exposure to synthetic chemicals begins in the womb, actually, as substances that our mother ingests while they're pregnant are transferred to us as babies. A 2009 study found 232 chemicals in the umbilical cords of 10 newborn babies that it tested. 9 of the 10 umbilical cords contain the chemical bisphenol A, leading researchers to believe that we are born pre-polluted. But remember that not all synthetic chemicals pose health risks. Roughly of the 100,000 synthetic chemicals on the market today, very few have been thoroughly tested. For the vast majority, we simply don't know what effects, if any, they may have on us. Synthetic chemicals travel through the environment in many ways. as we can see in this chart, from home, from work, from medical facilities and public spaces, agriculture, crops, and feedlots, from the soil, water, including surface and groundwater, and through the air. Silent Spring began the public debate over synthetic chemicals. In the 1960s, untested pesticides were sprayed with the assumption that they would not harm people. Rachel Carson's Silent Spring from 1962 showed DDT's risk to people, to wildlife, and to ecosystems. Remember, DDT is the chemical that was known to cause the eggshells of many top predators like bald eagles to become very brittle, causing almost the extinction, but definitely the endangerment of our national bird. Rachel Carson's Silent Spring was a bestseller and generated social change in views and actions towards the environment. It helped cause the banning of DDT in the U.S. in 1973, but developing countries with tropical climates still use it to control mosquitoes, because mosquitoes are the vector that carry the parasite that causes malaria. Many toxicologists focus on synthetic chemicals, but we need to remember that toxic substances also exist naturally. So don't assume that natural chemicals are all healthy and synthetic ones are all harmful. Plants, even our crops that we eat, contain harmful chemicals, and then we transfer those into our body when we eat them. Meat contains toxins that the animals got from the plants that they ate, and then as we eat the meat, it gets transferred into our bodies as well. Scientists are debating how much risk natural toxicants pose. Toxicants come in many different types, including the following: carcinogens, which cause cancer. They're hard to identify because of the long time in between the exposure and the onset of cancer. The link between cigarette smoke and cancer is an example. Mutagens cause DNA mutations. They can cause cancer and can harm sperm and egg cells. Teratogens cause birth defects in embryos. One example is a drug that was used in the 1950s called thalidomide. It was taken by pregnant women to prevent nausea and as a sleeping pill. Unfortunately, the drug turned out to be a terrible teratogen and caused birth defects in the babies that were born to the women who had taken the drug. And the birth defects included the misdevelopment of their limbs. The drug was banned in the 1960s then. Neurotoxins affect the nervous system, like lead and mercury, which can build up in our systems. Allergens overactivate the immune system. One hypothesis for the increase of asthma in recent years is that allergenic synthetic chemicals are more prevalent in our environment today. Allergens are not universally considered toxicants, however, because they affect some people but not others. Pathway inhibitors interrupt biochemical processes. For instance, rat poison contains a pathway inhibitor that stops the clotting of blood. Another example is cyanide. It kills by interrupting the chemical pathways in the mitochondria of our cells during cell respiration when we're trying to make energy. Most recently, scientists have recognized endocrine disruptors as toxicants. Endocrine disruptors affect the endocrine system, which is our system of hormones that stimulate growth and development and sexual maturity. They also help regulate functions like in the brain, appetite, sex drive, amount of water in our tissues, etc. Synthetic chemicals can block or mimic hormones like we've talked about earlier, BPA. Phthalates are another class of hormone disrupting chemicals that are unfortunately used widely in children's toys, perfumes, cosmetics, and many other items. Health research on phthalates has linked them to birth defects, breast cancer, and reduced sperm counts. Just like BPA, phthalates show how a substance can actually be all in one a carcinogen, a mutagen, and an endocrine disruptor. Organisms have natural defenses. Although synthetic toxicants are new, organisms have long been exposed to natural toxicants like mercury, cadmium, arsenic, and other harmful substances that are found naturally in the environment. Additionally, some organisms produce biological toxins themselves. These exposures have provided what's called selection pressure for mechanisms that provide protection from the toxins, meaning over time, natural selection has allowed organisms to be able to tolerate these harmful substances and have gained an evolutionary advantage. Skin and scales and feathers are a first-line barrier that prevent toxin intake, but through eating and breathing, these toxins can enter our body. In some cases, some organisms have biochemical pathways that can detoxify or metabolize the toxins and make them water soluble so they can be passed out of the body or excreted. Some toxic substances cannot be effectively detoxified or made water soluble, so instead the body quarantines them in the fatty tissues and cell membranes to keep them away from our vital organs. Heavy metals like mercury and dioxins and some insecticides like DDT are stored in the body tissues in this manner. Defense mechanisms for natural toxins have evolved over millions of years, but for these synthetic chemicals that haven't been around for so long, natural selection has not had enough time for us to make defenses against them. Different individuals respond differently to hazards. Genetics can have an effect on the response. People in poor health will be more sensitive to synthetic and natural harmful chemicals. Sensitivity also varies with sex, age, and weight. Fetuses, infants, and young children can be more sensitive. The U.S. Environmental Protection Agency, or EPA, sets standards for responses based on adult responses, so the standards might not be low enough to protect the young. The type of exposure affects the response. An acute exposure is high exposure to a hazard for short periods of time. They're easy to recognize, for instance, from an oil spill or a nuclear accident, and toxicity tests reflect the effects of the acute toxicity. Chronic exposure is a low exposure for a long time. They're more common, but they're harder to detect and diagnose. The effects are gradual. For instance, lung cancer and liver damage from alcohol abuse. So cause and effect may not be easily apparent. Toxic substances and their effects on ecosystems. When toxicants harm individuals, populations become smaller, and the decline affects other species then because of food webs and food chains. If predator species are affected, then the prey species can experience a population growth. If the prey species are affected, then we see a decline in predators as they've lost their food sources. Cascading impacts change the community's composition then and can threaten the ecosystem function. Toxins concentrate and persist in systems in many ways that we're still studying. Airborne substances can travel widely. For instance, chemicals can travel in the air, and the impact can be far from the actual site of use. And synthetic chemicals are found globally in Arctic polar bears and in Antarctic penguins and people in Greenland. We find chemicals within them. Pesticide drift is the airborne transport of pesticides. Toxic substances can concentrate in water. Runoff concentrates contaminants in surface water. Wastewater treatment plants release toxins, pharmaceuticals, and detoxification products from humans that can contaminate drinking water. Water-soluble chemicals can enter organisms through drinking or absorption, such as in fish and frogs and in stream invertebrates, can serve as an indicator of pollution because it affects them first. Contaminants in streams and rivers enter drinking water and the air, and the toxicants can move long distances through aquatic systems. Toxins can degrade quickly and can become harmless, or they may remain unaltered and persist for decades. Rates of degradation depend on the substance, the temperature, the moisture, and the sun exposure. Toxicants can degrade into simpler breakdown products that can be more or less harmful than the original substance. For instance, DDT degrades to DDE, which is also highly persistent and toxic. Toxicants can accumulate and biomagnify. Bioaccumulation is when the toxicants build up in the animal tissues and are fat soluble. So they build up in the fatty areas and in the cell membranes. They can transfer toxins to others through the food chain. Biomagnification is when the toxicant concentrations are magnified through trophic levels and have resulted in near extinction of organisms like the peregrine falcon and in bald eagles. Toxic substances can change the composition of ecosystems. They affect how organisms interact with each other and the environment and can threaten ecosystem services. Pesticides, for instance, have killed many bees, though the pesticides aren't intended for the bees, they're intended for other pests, but have nonetheless affected our major pollinators. So, farmers must hire beekeepers to pollinate their crops for them. Pesticides and antifungals kill decomposers and detritivores in the soil, again, even though these chemicals are not aimed at these organisms, they're affected anyway because they're in the area when they're applied. It's changed the nutrient cycling rates and reduced nutrients and caused slow plant growth. Determining the effects of particular environmental hazards on organisms and the ecosystem is a challenging job, and scientists rely on several different methods to do this. Scientists study the impacts of environmental hazards on wild animals to help conserve animal populations and also to understand potential risks to people. Often, wildlife toxicologists work in the field with the animals first before they go to the lab and test their hypotheses. For instance, some of the early work on tying environmental chemicals to endocrine disruption was done by biologist Louis Gillette. They discovered that alligators in lakes in Florida receiving agricultural runoff had higher rates of reproductive problems than the ones in less polluted lakes. Subsequent laboratory studies showed that contaminants found in alligator eggs, including the herbicide atrazine, could bind to receptors for estrogen and produce an enzyme that converts testosterone to estrogen. Following Gillette's work, researcher Tyrone Hayes, pictured in the picture off to your right, found in laboratory experiments that male frogs raised in water containing low doses of atrazine became feminized and hermaphroditic. They developed both testes and ovaries. Field surveys then showed that leopard frogs across North America experienced hormonal problems in areas of heavy atrazine usage. These studies indicated that atrazine, which kills plants by blocking biochemical pathways for photosynthesis, can also act as endocrine disruptors in animals. One way to gain much knowledge is by studying sickened individuals directly. The process of observing and analyzing individual patients is known as case history approach. Case histories have advanced our understanding of human illness, but tell us little about the probability and risk. For such questions which are common in environmental toxicology, we need what's called epidemiological studies. This compares a group of people who were exposed to a hazard to a group who were not. These studies can last for years. If rates of death, cancer, and those types of things are higher in the exposed group, the hazard may be responsible. It unfortunately does not show that the hazard caused the effect. Manipulative experiments can show causation, though, but unfortunately are unethical in humans, but are done in organisms like small mammals, rats and mice, etc. They're used because they elicit fewer ethical objections. The standard method of testing with lab animals in toxicology is called the dose-response analysis. Scientists quantify the toxicity of a substance by measuring the strength of its effects or the number of animals affected at different doses. The dose is the amount of substance the animal receives that's being tested, and the response is the type or magnitude of negative effects that the animal exhibits as a result. The response is generally quantified by measuring the proportion of animals exhibiting negative impacts. The data then is plotted on a graph with dose on the x-axis and response on the y-axis. This results in what's called a dose-response curve. Once they've plotted a dose-response curve, toxicologists can calculate a convenient shorthand gauge of a substance toxicity. A substance toxicity, or the amount of the substance that it takes to kill half of the population of study animals used, is called LD50. So again, the lethal dose for 50% of the individuals to die is termed LD50. A high LD50 indicates low toxicity for a substance, and a low LD50 indicates high toxicity for a substance. If the experimenter is interested in non-lethal health impacts, he or she may want to document the level of toxicant at which 50% of the population of test animals is affected in some way or other. For instance, what level of toxicant would cause 50% of your lab mice to develop reproductive abnormalities. Such a level, this is called the effective dose, 50%, or ED50. Some substances can elicit effects at any concentration, but for others, responses can only occur at a certain dose, or what's called a threshold dose. The shape of dose-response curves is important because estimating the effects on humans then often requires extrapolation, extending the dose-response curve beyond the doses tested with laboratory animals. Because extrapolations stretch the data beyond the actual curve, they introduce uncertainty into the interpretation of what doses are safe for people and which are toxic. Sometimes a response may decrease as a dose increases. Toxicologists are finding that some dose response curves are U-shaped and J-shaped and even shaped like an inverted U. Such counterintuitive curves contradict toxicology's traditional assumption that the dose makes the poison. These unconventional dose response curves often occur with endocrine disruptors like bisphenol A. It's likely because the hormone system is geared to respond to such minute concentrations of substances. Of course, it's hard to determine the harmful effects of single chemicals by themselves, but what about when different chemicals are mixed together? They may act in ways that cannot be predicted. Mixed toxicants can sum, cancel out, or multiply each other's effects. The interactive impacts that are greater than the sum of their constituent effects are called synergistic effects and occur often when mixed toxicants come together. For example, with Florida's alligators, lab experiments have indicated that DDT breakdown to DDE can either promote or inhibit sex reversal, depending on the presence of other chemicals. Mice exposed to a mixture of nitrates, atrazine, and insecticides have been found to show immune, endocrine, and nervous system disruptions that are not evident when just the chemicals are alone by themselves. So obviously it can be very hard for scientists to figure out what are all the effects of the different environmental toxins alone, let alone when they're mixed together. It's probably impossible to test all the possible combinations together. Unconventional dose response curves are presenting challenges for scientists studying toxic substances and for policymakers trying to set safety standards for them. Because so many novel synthetic chemicals exist at so many very low concentrations over wide areas, many scientists suspect that we may have underestimated the dangers of compounds that exert impacts at low concentrations. Scientists first noted endocrine disrupting effects decades ago, but the idea that synthetic chemicals might be altering the hormones of animals was not widely appreciated until the 1996 book Our Stolen Future by Theo Colburn and Diane Dumanovsky and J.P. Myers. Like Silent Spring, this book integrated scientific work from various fields and presented a unified picture that shocked many readers and brought criticism from some scientists and from chemical industries. Today, thousands of studies have linked hundreds of substances to effects on reproduction, development, immune function, brain and nervous system function, and other hormone-driven processes. Evidence is strongest so far in non-human animals, but many studies suggest impacts on humans. Some researchers suggest that endocrine disruptors may account for rising rates of testicular cancer, for undescended testicles in male infants, and genital birth defects in males. Others argue that the sharp rise in breast cancer rates, which is 1 in 8 U.S. women today, may be due to hormone disruption, because excess estrogen appears to feed tumor development in older women. Still, other scientists attribute male reproductive problems to elevated BPA exposure. For instance, Chinese factory workers that manufacture BPA have elevated rates of erectile dysfunction and reduced sperm counts. Research on hormone disruption has brought about a lot of debate. This is partly because of the scientific uncertainty and the youngness of the field, but because of the economic value of the chemicals being tested. For instance, Tyrone Hayes' work has met with a lot of criticism from the scientists associated with atrazine's manufacturer, because they would lose many millions of dollars if its widely used herbicide were to become banned or restricted. And now we return to the science behind the story with testing the safety of bisphenol A or BPA. Dr. Hunt at Case Western Reserve University in Ohio noticed that 40% of developing mice eggs showed problems with their chromosomes. Investigated it, and then they found that the lab assistant had washed plastic cages and water bottles with a harsh soap, and that the cages contained BPA. Her lab researchers recreated the accidental cage washing incident in controlled experiments then, and for the results, they found the developing eggs exposed to BPA through deliberately damaged plastic show significant problems during meiosis. In additional testing, the females received daily doses of BPA over 3, 5, and 7 days, and they had the same meiotic abnormalities, but at lower levels. The mice given BPA for 7 days were most severely affected. These findings were published, and hundreds of other studies of BPA at low doses have been documented and shown harmful effects in lab animals. And more scientists urge regulators to adopt the precautionary principle here and restrict bisphenol A. We express risk in terms of probability. Exposure to an environmental health threat does not invariably produce a given consequence. Rather, it causes some probability of harm, a statistical chance that damage will result. To understand a health threat, a scientist must know more than just its identity and strength. He or she must also know the chance that one will encounter it, the frequency with which one may encounter it, the amount of substance or degree of threat to which one is exposed, and one's sensitivity to the threat. Such factors help determine the overall risk posed. Risk can be measured in terms of what's called probability, a quantitative description of the likelihood of a certain outcome. The probability that some harmful outcome, for instance, injury, death, environmental damage, or economic loss, will result from a given action, event, or substance expresses the risk exposed by that phenomenon. Our perception of risk, though, may not match reality. Everything we do involves some level of risk. We try to minimize that risk, but perception may not match reality. For instance, most of us perceive flying in an airplane as riskier than driving a car, but statistically speaking, plane travel is actually much safer. We feel more at risk when we don't control a situation, so we fear nuclear power and toxic waste, but not smoking or overeating, though these voluntary activities are actually shown to pose far greater health risks. Risk assessment is the quantitative measure of risk. It compares risks involved in different activities or substances. It identifies and outlines problems. It helps determine which substances and activities pose health risks to people or wildlife. Risk assessment has several steps. The first steps involve the scientific study of toxicity that we've examined before, determining whether a substance has toxic effects, and through dose-response analysis, measuring how effects vary with the degree of exposure. Subsequent steps involve assessing the individual's or the population's likely extent of exposure to the substance, including frequency of contact, concentrations likely encountered, and the length of the encounter. Accurate risk assessment is an important step toward effective risk management. It consists of decisions and strategies to minimize risk. Federal agencies have helped us to manage risk. For instance, the U.S. has the Centers for Disease Control and Prevention, or the CDC, the EPA, or Environmental Protection Agency, and the FDA, or Food and Drug Administrations. Scientific assessments are considered with economic, social, and political needs and values in risk management. Comparing costs and benefits can be hard. Benefits are economic and easy to calculate, but health risks or the costs are hard to measure, and probabilities of a few people suffering versus lots of people not suffering are hard to quantify. Risk assessment aids in risk management. The end result of risk management is a policy decision that minimizes the risks of environmental hazards. Two approaches exist for testing the safety of new products. For instance, the innocent until proven guilty approach can be employed. It assumes a substance is harmless until it's shown to be harmful. It promotes technological innovation and economic activity, but allows dangerous substances to be used. The precautionary principle is another. It assumes a substance is harmful until it's shown to be harmless. It identifies troublesome toxicants before they're released to the public and to consumers like you and me, but can impede the pace of technology and economic advancement. One might then ask, who should have to prove a product is safe? The manufacturers or government and citizens? European nations have recently embarked on a policy course that incorporates the precautionary principle, whereas the United States mostly follows the innocent until proven guilty approach. In the U.S., several federal agencies are assigned responsibility for tracking and regulating synthetic chemicals under various legislative acts. The FDA, or Food and Drug Administration, under an act first passed in 1938, monitors foods and food additives, cosmetics, drugs, and medical devices. The EPA, or Environmental Protection Agency, regulates pesticides under a 1947 act and its amendments. The Occupational Safety and Health Administration, or OSHA, regulates workplace hazards under a 1970 act. Several other agencies regulate other substances. Synthetic chemicals not covered by other laws are regulated by the EPA under the 1976 Toxic Substances Control Act, or the TSCA. Again, this act was incorporated in 1976. The EPA monitors chemicals made in or imported into the U.S., and the EPA can ban substances that pose excessive risk. Many health advocates think the TSCA is too weak, that industry screening is minimal. They want to push for more testing, and toxicity must already be proven, but testing is minimal. Only 10% of chemicals have been tested for toxicity, and fewer than 1% are regulated, and almost none have been tested for endocrine, nervous, or immune system damage. So, they say the EPA regulation is only partly effective. A frequently asked question is, if the government allows a product to be sold in stores, isn't it safe? Just because a product is available to the public does not mean it poses no risk to consumers. Some dangerous products like firearms and cigarettes are recognized to be hazardous and have restrictions placed on their purchase. Medicines, cosmetics, and some types of food undergo testing for safety prior to release, but other potentially dangerous products like endocrine disrupting chemicals and plastics are not similarly tested. We've seen that the U.S. government's approach to regulation relies more heavily on the recall of products found to be dangerous than on the testing of the products before they reach the market. Hence, it would be a mistake to assume that the products you purchase have been thoroughly tested prior to their arrival on store shelves. The European Union, or the EU, is taking the world's boldest step toward testing and regulating manufactured chemicals. In 2007, the EU's REACH program went into effect. REACH stands for Registration, Evaluation, Authorization, and Restriction of Chemicals. It shifts the burden of proof for safety from the government to the industry. It requires that certain chemical substances produced or imported in amounts of over 1 metric ton per year be registered with a new European Chemicals Agency. The world's nations have also sought to address chemical pollution with international treaties. The Stockholm Convention on Persistent Organic Pollutants, or POPs, POPS, came into force in 2004 and has been ratified by over 150 nations. POPs, POPS, are toxic chemicals that persist in the environment. They can bioaccumulate and biomagnify up the food chain and can travel long distances. PCBs and other contaminants found in polar bears are a prime example of these POPs. Because these often cross international boundaries, and international treaties seem to be the best way to deal with them fairly. The Stockholm Convention aims first to end the use and release of these 12 worst POPs, which are known as the Dirty Dozen. They're the most dangerous. It sets guidelines for phasing out these chemicals and encourages transition to safer alternatives. In conclusion, there's been international agreements that show that governments are working to protect society, wildlife, and ecosystems from toxic chemicals and environmental hazards, but solutions need to be more than government regulations. We found that consumer choice affects industries. Once scientific results are in, society's approach to risk management determines what policies are enacted. A safe and happy future depends on knowing the risks that some hazards pose, and then replacing those hazards with safer ones.